In chapter 2 and 3, we talked about kinematics and dynamics of particles. In chapter 5, we talked about kinematics of rigid bodies. And finally, in chapter 6, we are going to talk about dynamics of a rigid body. So, if we have a rigid body with the centroid of G, let's say we have a bunch of forces on it, like F1, F2, it can be anything, F3, and maybe some moments like M1, M2, and maybe more. Then what are going to be the dynamical equations for this rigid body? Probably all of you know the second law of Newton. Sum of the forces on any rigid body, or in general on any system, is going to be equal to the mass times acceleration of that rigid body. But you should be careful here. What acceleration? In chapter 5, you saw we have different accelerations for different points on a rigid body, right? Acceleration of center of gravity is going to be different than acceleration of this point. So in Newton equation, when we are talking about acceleration, we mean acceleration of the centroid. So sum of the forces is equal to mass times acceleration of the centroid. And you can break down this equation to in different directions. For example, if you are using xy plane or xy coordinates, you can split this equation to sum of the forces in the x direction is equal to mass times acceleration of the centroid in the x direction. Sum of the forces in the y direction is equal to mass times acceleration of the centroid in the y direction. And if you have z direction, same thing for the z direction. In general, sum of the forces in any direction, like for example this random direction, is going to be equal to the mass times acceleration of the centroid in that specific direction. So this is true for any direction. So for example, if you are using normal tangential coordinate, you can write these equations as sum of the forces in the tangential direction is equal to mass times acceleration in the tangential direction. Just to remind you, acceleration in the tangential direction was speed dot or v dot. And acceleration in the normal direction is equal to mass times acceleration of the centroid in the normal direction. And again, just to remind you, acceleration in the normal direction is equal to velocity squared divided by rho. And if you are using polar coordinates, you can write the Newton equation as sum of the forces in the radial direction is equal to mass times acceleration of the centroid in the radial direction. And again, to remind you, acceleration in the radial direction is r double dot minus r theta dot squared. And sum of the forces in theta direction is equal to mass times acceleration of the centroid in the theta direction. And a theta is r theta double dot plus 2 times r dot theta dot. In general, as I told you, sum of the forces in any direction is equal to mass times acceleration in that direction. And when we are saying acceleration, we mean acceleration of the centroid. This is not, these are not all the equations. We have one more equation. By the way, in this class, we are going to talk about only 2D problems. In 3D, the equations might be a little bit different and more complicated, but the essence of all of them is the same. So what is the last equation? What is the other equation that we need to solve dynamical equations? Is sum of the moments. In statics, if you remember, whenever something is moving with a constant velocity, or it is in a stationary condition, which we call it a static condition, you have the sum of the forces is equal to 0. Sum of the forces in any direction is equal to 0. And sum of the moments about any point is equal to 0. So this is moments about any point is equal to 0 if you have a static condition. But in dynamics, equations are going to be slightly different. Sum of the forces is equal to mass times acceleration, which we talked about that. And also we have something about the moment too, similar to statics. In dynamics, sum of the forces is equal to mass times acceleration of the centroid, and sum of the moments is not equal to 0. Sum of the moments is equal to mass moment of inertia times angular acceleration. And we should be careful about this equation because this is a very common mistake that the students do all the time. Sum of the moments about different points is not equal to I times alpha. Sum of the moments only about the centroid is equal to mass moment of inertia about the centroid times alpha. Alpha is the angular acceleration of the rigid body. G is the centroid. Ig is the mass moment of inertia. About the centroid. We should know how to calculate the mass moment of inertia. We learned it in Appendix B. And also we can use tables. For more complicated geometries, it is possible to find the G, to find the I using the tables. So these are general equations. Actually, these are the most important equations that we have in this chapter 6, and you are going to be able to solve a lot of problems using these equations. To show you how it works, I'm going to start with a simple problem. Problem 6.1. Here we have this rod which is pinned to another body at point O, and also we have a roller here to support it, and everything together is moving to the right with acceleration of A. And here we are supposed to find the forces at point O. Acceleration is given. Acceleration is equal to 20 meters per second square. And we know the mass of this guy, this bar. M is equal to 30 kilogram. And it is uniform. So everything is moving to the right with acceleration of 20 meters per second square. And we are supposed to find the reaction forces at point O. So I would suggest to think about this problem for like 5 minutes before seeing the rest of the video. So to solve any dynamic problem like this, the first and most important thing that we need to do is drawing the free body diagram. So I'm going to draw the free body diagram of this bar. We have this bar, this is point O, this is point A, and this is B. And in free body diagram, we have to show all the forces that we have here, right? Here we have a pin. So whenever you have a pin, it is possible to have force in two directions. I'm gonna call them OX and OY. And here we have a roller, and this roller can apply force to the bar in that horizontal direction. So all of these forces are unknowns, right? We don't know what is force A, we don't know what is OX, and we don't know what is OY. So if you list the unknowns, it usually helps you to figure out, for example, how many equations you need, and in general, what we are doing. So Whenever we have a free body diagram, we have to define the coordinate. In this problem, I'm going to use xy coordinate. So I have three unknowns. I need three equations. And the only equations I have here is the Newton equations. Sum of the forces is going to be equal to 0 in any direction. So let's start by, sum of the forces in any direction is equal to mass times acceleration in that direction. It's not static. So sum of the forces in the x direction is equal to mass times acceleration of the centroid in the x direction. Always write the equations before putting the numbers or the value of the forces. So what forces do we have in the x direction? We have OX and also we have A. So OX plus A is equal to mass times acceleration of the centroid. Because this bar is just uniformly moving, all the points of it is moving to the right, and there is no rotation. Acceleration of all the points on this bar is going to be the same. You are moving with the same velocity, same acceleration. We have a pure translational motion here, right? So acceleration of the centroid is going to be equal to the acceleration of this L-shaped part. So acceleration of the centroid is going to be the same thing, 20 meter per second squared. So it's going to be mass times that's A, and A is equal to 20 meter per second squared. So we got one equation. Next equation, sum of the forces, let's write it here. Sum of the forces in the y direction is equal to mass times acceleration in the y direction. In the y direction, we have only OY, and also I forgot something in my free body diagram, the weight, mg. In the y direction, we have OY in the positive direction and also mg in the negative direction, so minus mg is equal to mass times acceleration in the y direction. So this part, as I told you, is moving purely in the x direction. So there is no movement, there is no velocity, there is no acceleration in the y direction. So it's going to be mass times 0. So it is 0. Second equation. But we have three unknowns. The last equation is going to be sum of the moments about this centroid is equal to I about the centroid times alpha, angular acceleration. So centroid is here, G. We need to find the moment of all the forces about it. So we have four forces, mg. The moment of mg about g is equal to 0 because it is passive rate. Moment of OY about g is 0 again. It's not making any moment about it. Moment of A about G is going to be A times this distance, right? And what is that distance? If you look at this plot, the centroid is going to be here. It is 2,000 millimeter from the top, or 2 meter from the top. So it's from here to here is going to be just 1 meter. So 1 meter. Force A times the distance, 1 meter. And the direction of the moment using right-hand rule, or you can simply say if you want to rotate A about G, it's going to move in counterclockwise direction. So it is a positive moment. So I'm going to have A times 1, moment of A. Moment of OX is going to be OX times the distance, which is 2. So OX times 2. And again, it is making a positive moment. So I'm going to have OX times 2 is equal to IG times alpha. Alpha is the angular acceleration of this bar. This bar is moving it has just purely translational motion. It is not rotating. So angular velocity, angular acceleration, all of them are equal to 0 for this body. So Ig times alpha is going to be equal to 0. Whenever we have a body which is purely has translational motion, no rotation, alpha of it is going to be equal to 0. So we got three equations, 1, 2, and 3. Three simple linear equations. if you combine all of them together, 1, 2, and 3, you can find all of those forces. And I'll let you to calculate that. You can use your calculator. If you do that, A is going to be equal to 1200 Newton, and OY is going to be equal to mg. And OX is going to be equal to 600 Newton.